So for order, we just introduced it. Order, two ways to think of it. It's the number of elements. It's the number of elements in G, or you can think of it as the smallest integer m, for which A of m equals E. We gave the example here of a group Z on addition, operation of addition, and we're looking at element 2, and we found the identity was 0. So since the identity was 0, we looked at the order of 2. 2 operated once, twice, 3 times until we got the identity 0. So the order of 2 on this operation is 3. So let's try this with a different one. Now we have, on the next page, you see where it says R, real numbers, operation what? Addition, and now we still keep the same identity, 0, but we're going to use, and still use 2. But what do you think this one is going to be for an order? Well, if we go 2 to the first, you get 2. That's not 0. What's 2 to the second without any mods? 2 plus 2 is 4. That's not 0. What will 2 to the third be? 2 plus 2 plus 2 is 6. That won't be 0. And so you keep going forever. You will never get 0 if you keep adding 2. So this is what we would call, there is no m such that 2 to the m or 2 times m equals 0. So we'd say 2 has an infinite order. And I don't see that happening very often, but it's nice to have a definition for it. Does that infinite order make sense? Okay, so then a finite group is a group with finite order, which is a group containing a finite number of elements. Infinite is what we just showed you, where the group contains an infinite number of elements. This is an interesting theorem. I want you to read it and tell someone next to you what it means. All right, so who has an idea of what this means? Amanda, go ahead. Vishal. Did they set you up? They set you up. Go ahead. Oh, Amanda, go ahead.
So if the group is defined as not like all of the numbers possible, then each of the elements in the group would have a defined order and it wouldn't have a
So you're saying, kind of emphasizing what I just said at the beginning, is that elements in the group, when you look at the order, are different than the order of each element. So did I say that right? Order of each element. The number of elements in the group, that's right. The number of elements in the group, order of each element. So as it seems different, it really does come together that if you do have a finite number of elements, that order of the elements of the group, each one inside is going to also have a finite number. But if one of them is infinity, they'll all be infinity, both the number of elements in the group and the order in each one. So one falls into the other. So they did a kind of a, I'm not impressed with this proof. It's not very efficient. But what they did is they showed you, what if you showed that a to the m plus 1 equals a to the m plus 2? And I think they're doing this counterexample. And then they looked at combining the inverses next to them, and things would cancel out to give you, if you have a inverse times a, those together make e. And so the more times that happens, eventually you get e. Eventually you're going to get that e equal to a to the m2 minus m1, and m2 minus m1 is going to be the integers. I'm not sure this proof really helps a lot, but what they're saying is that if you have a finite number of elements, that will fall through with your order. Here's two other theorems that I think are not proven very well here. This one, I'd really be interested in what you think is going on with this. A star A inverse equals A inverse A star, or star A equals E. This is what we started with. How did they get this? Anybody see how they went from here down to there? I get this. This is the definition of inverse. But what's happening there? Yeah, I know, but how does this justify that? If you figure it out, let me know, because it does not make sense to me. Anybody see it? I'll let you do that. But we're going to do a quick example, example 50. Great review for the quiz, and it'll be a great sum up of orders. We're going to find the order of 0, 1, 2, and 3. But here's what I want you to do. See if you can complete as much of this as possible without my help. So which is probably the easiest thing to determine of closure associative identity on the Cayley table? What's the easiest thing? Closure. So let's see what you have there. For closure, you're always going to list for all A, B, an element of. You want to write what it's an element of. So if you didn't do that, would you write for all A, comma, B, element of? We're looking at all the Z's that they gave us here. A, B is an element of Z4. Then what's this part here? Operations. So you list the members that exist and the operation. Then you draw your conclusion. So we did that. We listed the elements. We listed the operation. Now say, and this is inefficient. I don't think this is complete. All elements exist in each column and row on the Cayley table. That's how we would say. What's that? Yes. Yep, you need all 0 through 3 in each row and column to be closed. And it is a Latin square, yep.
If it was like all 3, it would still be closed.
If you had 3, 3, 3 here?
Yeah.
No, because this one wouldn't have the 0, 1, and 2.
No. Closed just means that elements of the first set go into like the column. The entire table was just full of zeros. It was just full of zeros.
Nope. No, it needs to have all the to be closed. Each value has to exist under each operation. That's the definition of closure. So associative is easy for this because what operation are we using? We're using addition. So you can say associative follows the property of addition. So since it's an addition, it is associative on Z. Notice they also added the where it's an addition on. It's on Z or in Z. What did you do for the identity with the Cayley table? You looked at these two or these two. If these are the same and these are the same, right up here and here will reveal what your identity is. So for all A element of Z4, you write the operation 0 plus A or A plus 0 is equal to A. Then 0 is the identity element. Now, for the inverse, if you have the identity element, you want to see where is 0 coming up. And this one you're really good at. For the inverse, 0 is going to be the inverse of itself, and what else? 2. So 2 and 0 are its own inverse. And 1 and 3, what are 1 and 3? Yeah. And then you can say, therefore, and I like it when they put Z4 and plus 4. In other words, the integers, modular 4, plus 4. I don't know why they have the 4 here, but Z plus 4 has all 4 axioms, so therefore it's a group. So it's a group because all 4 axioms hold. what do you use on the Cayley table to tell you that it's going to be a commutative or abelian? Diagonal. So we've got that. So from the diagonal of Cayley table, along the main diagonal, a plus b equals b plus a. So you can say on the Cayley table main diagonal, a plus b and b plus a are equal. That's that symmetry. I'd even say symmetrical along the main diagonal. That's all you need. And then don't forget, AB is an element of Z4. And then the last part, I think this is the last part. Yeah, therefore it's abelian. Now we're going to do the order. To state the order of each one using the Cayley table, this is where it gets good. So what's the identity element? 0. So what you're going to do is you're going to take each one of these, starting with 0. Is 0 the identity element? So it's an order 1. So you would say that 0 has an order of 1. Now let's do 2, or 1. Is 1 0? Is 1 a 0? It's a dumb thing, but is 1 equal to 0? No. So it is not an order 1 isn't an order 1. But how about 1 1? What will that be? 1 1. 1 1 is 2. Is 2 equal to 0? Nope. So 1 plus 1. How about 1 plus 1 plus 1? Or in other words, we did, here's 1, and then we did 1 plus 1, which is 2. Now do 1 plus 2. What do you get? 3. Either way. It's funny you should say that because this is really what we did what I did originally, and I switched it to this way. I'd start up here, but anyway, so you did 1 plus 1 was 2, 1 plus 2 is 3, 1 plus 3 is what? 0. So 1 is your first order, 1 plus 1 is the second order because you're adding 2. 1 plus 1 plus 1 gives you the 3, and 1 plus 1 plus 1 gives you 4, so that is going to be order 4, right? So 1 has an order of 4 because 1 plus 1, 1 plus 1 plus 1, none of those are 4, but when you add the fourth one, it works, so it's order 4. Might make more sense when we get to 2. Let's do 2 next. Is 2 equal to 0? No. How about 2, 2? Yes. So therefore, what's the order for 2? 2. Am I losing you? What do you think 3 is going to be? Well, you almost have all the answers. 3. So 3 is an order 1. 3 plus 3 is 2. That's not it. 3 plus 2 is 1. That's not it. 3 plus 1 is 0. So there, it's going to be a what? Order 4. It's an order 4. Okay, watch this. No, you're doing fine. It's just a little confusing. 3 plus 3 plus 3 plus 3. What's that equal to?
12.
12. Mod 4 would be 0 mod 4, right? Now, you can do this on the Cayley table by going 3 and 3 plus 3.
Like you started 3 plus 0. You started 3, 0, and it's 3. So then 3 plus 3, which becomes 2. So then 3 plus 2. What is that? 1.
Yep. And so when you added 3 plus 3, when you added these two, you get a 2, right? So now I'm going to go, and you could go 2 plus 3. It doesn't matter. And so if you went 2 and then came down to this 3, you're going to get 1. 3, 2. That'll be 1, right? So what if we added 1 more? 3, 1. There's your 0. So that's when you get all of those. Isn't it weird? It's kind of weird on that table. And easy to mess up. So let's try it one more time. One more time. 3 plus 3 is 2. Okay, so then 2 plus 3 will give us 1, and then 3 plus 1 will give us 0. That's order 4. Yes? Okay, so we found the orders. We found all that. Just wanted to bring your attention to this one. This is, we did the cis thing yesterday. We changed this into z equal to 1 cis 2 pi over 3. And we played around with it a little bit. We looked at z squared, which was cis 2 pi over 3 to the second. What did that do to 2 pi over 3? Changed it to what? 4 pi over 3, didn't it? Okay. And then when we did z cubed, it's going to be cis 2 pi over 3 cubed, and that changed us back to cis 2 pi, which is going to be equal to 1. And so what they're doing here is they have alpha, alpha squared, alpha cubed, alpha to the 4th. And then what they did is they showed you what these represented. And then when they did that, they went, oh, okay, let's put it in a Cayley table and multiply them together. So here's 1A through 5, 1A through 5. You do 1 times 1, 1 times alpha, I call it z, 1 times alpha squared, and you build this Cayley table. Is this Cayley table closed? Each row and column, do you see 1A through A5? Yep. Okay, so that's good. And you can look at all the other things. It's multiplication, it's associative. The identity is definitely 1 this time. But, and you could show those. Let's go down to the order, though. Would you go down to the bottom, and I want you to list 1, alpha, alpha squared, alpha cubed, alpha to the 4th, and alpha to the 5th, and I want you to find the order of each. So we're just reviewing the order. The proof is pretty straightforward, but for 1, is 1 the identity element? E equal to 1, yeah, so this is an order 1. What will alpha be? How many say 6? Hannah, what do you think? It's weird, isn't it? Let's try it. Let's do this one. Is alpha equal to 1? No, so it's not 1. Now do alpha times, alpha times alpha, what do you get? Alpha squared. Then you take that answer, alpha squared times alpha gives you alpha cubed. So we have 1, 2, because it's alpha times alpha, that's 2. Then it's 3, then it's 4, then it's 5, and are we going to make it to 6? Yes, 6. It's so weird it makes sense. So this is going to be order 6. You have to go through all of those until you get it. But what about alpha squared? What's that going to be? 3? Let's see. How many say 3? How many say less than that? How many say greater than 1? How many say less than 3? For 2. Okay. Alpha squared times alpha squared is what? Alpha to the 4th. Then you go alpha squared times alpha to the 4th And so this is 1, 2, 3. Order 3. And alpha cubed. Alpha cubed. Well, this is the best one. It's 2, isn't it? Order 2. Alpha to the 4th. This one might be a little more work here. 1, 2. Nope, not that bad. Order 2. And how? Did I miss something? Was that 3? Was that 3? Alpha 4 would be 1, 2, 3. Excuse me, 3. Yep. And then alpha to the 5th is going to be 1, 2, 3, 4, 5. I did it wrong. 1, 2, 3, 4, 5, and 6. Yep. So that's order for you. The problems that you're going to be working on, here's a group problem that we're going to work on, and then the homework's going to be 2 and 3.